the simplest aim here we take, that it is to estimate the power spectral density of a discrete time random process by using the periodogram technique here. For the demonstration of the periodogram technique, we first of all require a random process here. Now, the generation of the random process that we have not demonstrated into the previous chapter, as with the MATLAB environment we are very familiar from the first chapter, the digital spectrum. Various signal processing tasks we have demonstrated into the MATLAB environment. In the second chapter also, that it was dedicated to learn the multi-rate signal processing. Thereupon also we have worked into the MATLAB environment. For the third chapter we have not done it. We have taken that chapter to see what are the fundamental details, so that the power spectrum estimation, the core area of our subject, advanced digital signal processing, will get easier to understand. Now here we shall have the first task as to generate a random process. So random process is basically a signal here. As we have seen that the basic denotion of the random process into the discrete time domain especially can be by x of n here. So we take the variable with the name x to denote it. We have already seen the difference between the deterministic signal and the random signal, from which we have all this to be a random process here. So in general, by the use of the trigonometric functions, for example, we can have the generation of the signal that I can show you. If we take the amplitude to be, for example, 0.5, that is multiplied by the trigonometric function, that is function, and within the parenthesis here we show 0 to 99. So total 100 samples we expect into the discrete time axis here, and that is to be multiplied by the variable phi, the constant it is, divided by 16, for example, if you take. So this will simply denote a discrete time signal here. Now if you like to have what exactly the signal we have generated, for plotting purpose we can make the use of stem function. So stem, the input, that it will be x here. So if this much of program we will like to save, so onto the desktop we can select the ADSP to be the folder here, and hereupon we can name it by the name. Here we can execute underscore peri for periodogram here. So we have saved this. The title to this untitled tab has been changed to the name that I have given. Now if you can run this particular program, yes, we have to change the folder, and now you can see into the folder where we have saved this file, the ADSP folder, the execute peri here, this is the M file that has been generated, and now this is what the figure has been displayed here. Before looking at the figure, we can focus our attention onto the workspace, where onto the right hand side we have the variable x generated. Before that it was the empty workspace, and now the x is holding the dimensions 1 into 100 and the type is of double here. Now when we look at the figure, so I maximize this particular figure. So here we have plot. Now onto the horizontal axis we have the discrete time intervals plotted here. So right from 0 to 100 we have all these values, and the amplitude levels onto the positive side as well as onto the negative side we have. So directly we can see this is nothing but a cosine wave, as it starts from the positive maximum amplitude here, that is 0.5, that we have multiplied to the cosine function, and with the specific intervals it goes to the 0 level, and again into the negative side we have the half cycle of this sinusoidal wave, and this goes on the repetition here. So now I shall close this window. So this way we can simply generate a signal, and we can also visualize what way the signal has been generated here. Now we require the random signal here, so that we can have the spectral estimation for that random process by the use of periodogram technique here. Now instead of using the step and this one that I am going to comment here, if we mix the two signals so that the randomness can be introduced here, I can have the x assigned by, for example, the amplitude I take for the first component 0.8 that I multiply to this time the sine function. Again I can take the samples 0 to 99, that it is 100 samples, and for the harmonics it will be multiplied by the constant pi, this time divided by 8, for example, we take. So this is what the same way we have into the previous step. Now we add one more component to this one. So now, for example, the amplitude level will be quite higher, 1.5 we take, that is multiplied to this time the cosine function, and it also holds 0 to 99, that it is the 100 samples, and this time we have pi divided by 4. So this will be giving a particular frequency to this periodic signal component here. So two periodic components we have added to each other here. So this change I save. So X has the two frequency components, and let us check how this will be visualized graphically. So we make the use of stem function and let us run this particular one. So now this figure gets visualized here. Into the workspace, the same variable holds the information X. Now it has been displayed. So again onto the horizontal axis, right from 0 to 100, we have all these particular discrete time intervals and the specified values here you can see. So this is not exactly the simple sinusoid here. It is a mixture of the two sinusoids having the two different frequencies and the two different amplitude levels. So amplitude levels you see nearby to the value 0.5 are from the first component here, whereas those you see nearby to 1.5 are from the second component here. So this is what the periodicity we have manipulated from the first example to this example here. So this window we close. So we are not also going to make the use of this X to be the random process here. So there is no use of stem here. Now another technique to have generation of the random process is directly assigning the values of the amplitude levels to this X here. So it can be assigned into the array form, that is why we take a pair of square brackets here. The values in general we can give like 1.2 space, here we have 0.7 space 0.2, next to that we can make the use of 0.4. Now after this we can make the negative values also assigned. So minus 0.7 we go for, next to that 1.8, next we can go for 0.1, very small value close to the horizontal axis, then 1.9, 0.3. randomly we can give any of the values, so that time we can call this to be a random signal here. Now again going for the negative values in the downward side here, 0.8 we will like to give in the negative, next to that we can give in the positive side 1.3, minus 0.7, again we can extend with 0.6, next to that minus 0.3, minus of 0.1, next to that we can go for minus, we have 1.2 here, next minus 0.3, 1 we can go for 0 value, we can go for minus 0.9, next to that minus 0.8, in the positive side again 0.9, we can go for 0, we can take half, that it is 0.5, 0.4 we can take. So this way we are going to increase the number of samples associated to this random signal into the discrete time domain. After the 0.8 I can give it 0.4, then minus 1.3. Next to that again let us take 0.4, 1.2, minus 0. Here we take 4, 0.01 we can take, 1.21 we can take. So I suppose these many samples are enough here. So more than 30, I think it is 35 we have assigned to. So let us see how exactly such a random signal assigned to X can be visualized here. So we save the changes, and after saving we will try to run this particular program. Yes, now as I maximize this window where the assigned signal has been plotted, now you can see onto the horizontal axis right from 0 to 35 we have the discrete time intervals here. Now the first one we can see here that it is having the X value is equal to 1 and Y value is equal to 1.2. So this is the first sample holding the amplitude 1.2 onto the vertical axis. Next to that continuation from the last sentence. Next to that we can see the second one holding the value X is equal to 2. The amplitude here it is 0.7. Next to that we have X is equal to 3, Y value is 0.2, then Y value is equal to 0.4. This is the fifth sample holding the amplitude in negation side here minus 0.7. In the similar case onto the 11th sample, here we again have the negative value minus 1.5. We have minus 0.8 onto the 12th component. So this way we have the random nature of amplitude that has been assigned to the variable X. So this time we can say this is nothing but the generation of a random process here. Now there are another ways also with the help of which we can have the generation of the random process or the values to any of the variable to generate the signal here. For example, if we can have X assigned by, let us say, the array where we make the use of MATLAB functions. For example, once 1,35 if I assign, next to that if I write function zeros, again we take the same length 1,35. So this way we can have the use of ones and zeros, and with the proper length provided to them we can also generate the random signal. So this is not the exact random signal here. Now we can visualize what we have done here. So stem input it will be the X. So saving the changes and running the program here. So now you can see here right from the first sample to the 35th sample we hold the value of the amplitude 1 for each of the product samples here. Whereas right from the 36th sample to the 78th sample, here we have the amplitudes denoted by 0, Y is equal to 0 here. So only 2 times we have made the use, once for the function ones and then for the zeros here. Now we can also have the another function into the use. So this I am not going to make the use of. Now that function here we can write, the information can be seen. So this is mostly used for the purpose of generating a noise signal here. So we can make the use of help command onto the command prompt. Here you can see this is the function randn. So normally distributed pseudo random numbers can be assigned here. So we don't have the exact pattern with which this is supposed to assign the values to the given variable here. So now if we can make the use of it, we can write X is equal to the function here randn, and within the parenthesis we can specify the length only. So 1,100 we go for semicolon to suppress its output here. And now if we can make the use of stem to visualize, so that time saving the changes and running this particular program. Now as I can see these are the random samples, 100 into the number. Onto the horizontal axis you can see 0 to 100 here. The first sample you can see it is x is equal to 1. The amplitude level you must remember for comparison purpose 0.5377, whereas the second one is 1.834. The third component is into the negative value of amplitude minus 2.259. If I close this window and without making any changes to this script here, if I run it again, now you can see here the values have got changed to again the 100 samples here. So we have the first one holding the amplitude level this time 0.8408, whereas the second value of the discrete amplitude here it is 0.888 into the negative side here, whereas into the previous case that it was the positive amplitude. The third one here it is positive 0.1001 here. I again close it and without making any changes I run this particular program. So again we get another random pattern generated here. So now this time the first sample is holding the amplitude 0.1832, whereas the second one holding minus 1.03, third one has the amplitude 0.9492 here. So here while programming for demonstration of the spectral estimation using the various techniques that we are going to see in this particular chapter, I shall be making the use of this particular function that has been assigned to x here. Now we shall move forward here. Now the purpose of this particular task to generate a random process is now completed here, and that we have visualized also. Now there should be the another module where we can have the spectral estimation. So here I write the module specified spectral estimation. So now as we are covered with only one spectral estimation technique, that it is periodogram here, now we shall be generating a function with the same name periodogram here. The output of the periodogram is nothing but the estimate of the power spectral density, and for power spectral density we usually use the notation capital P, to the suffix of which we denote process denoted by. So to the suffix we have generally x here. So as we have generated the random process and denoted it by x here, so let us expect the output of the function to be px, that we can obtain by the help of the function that we shall be developing here. So we write here periodogram. To this periodogram we shall be assigning the input as the discrete time random process that we have generated into the earlier steps, and also now we are going to have the assignment the specific range of the samples, as in the earlier step we have generated 100 samples into the random process here. If you want to operate the periodogram spectral estimation technique onto the specific range, for example let us say from 10 to 15, we can make the assignment here. So we compress its result here, and by the next step we shall be having the plotting of this periodogram here by the various ways, definitely we can say. So now I just save the changes to the script here. Now this periodogram function is not into the existence that we have to develop here. So for that purpose let us take the another script here, and this script we shall expect it to be the function, hence the first keyword it will be the function here, and the function output as we have already discussed, it will be the power spectral density of the discrete time random process, in general expected denoted by x of n, hence I noted by px here, and the name of this function it will be periodogram, and the inputs we can specify x as the discrete time random process, and the range of the samples we start at first of all n1 and end at n2 here. Next to that the last sentence should be the end here. So this is what the body of the function. Now let us save it by the same name. So this is the name periodogram.m, and it will be a function that you can see into the current folder. Here it is the function denotation, whereas this is the main script here where we can call this periodogram function here. Now we have not defined or assigned anything to the x, n1 and n2 here, that we shall develop here. So this is basically the function for the spectral estimation using the periodogram technique here. Now the x here is the input sequence, so that we are going to make the use of. N1 we specify as the starting index here, whereas the N2 is the ending index. And if we don't specify the values of the N1 and N2, so that time this function, the periodogram, will be operated onto the entire sequence, discrete time sequence here. So as we accept continuation, so as we expect the input to be the discrete time random process x, we will like to assign it with all the components there. Hence within the parenthesis I put the colon over here. So x is accepted as the input. Now looking at the number of arguments that we can accept to this particular function, we write the if condition nargin, and if it is equal to 1 here, so that time we can specify n1, the starting index, to the value 1, whereas n2, that it is the ending index, we shall specify the length here, and this length is for the discrete time random process that we have generated into the earlier script named by the execute underscore peri. So this if condition we are going to end here. Now after that we have to have computation of the power spectral density by the use of periodogram technique here. So the output as expected to be assigned to capital P small x here. So here we compute it as the absolute of, hence the function ABS. The Fourier transformation, here we are going to make the use of fast Fourier transformation. The MATLAB syntax, here it is FFT here, and now here the FFT will be provided the input as the discrete time random process x specific to the range n1 to n. So this range has been specified by the use of colon here. Now we can get it for 1024, and further it is multiplied by, so it is given the power, so dot, and the power here it is provided, it is 2 divided by, within the parenthesis we specify n2 minus n1, which is added to 1 here. So this formulation we have done with respect to the probability, with respect to the power spectral density estimate that we have seen into the previous video, and here we can have the assignment px of 1 is equal to the px of 2 here. So we end this line with the help of semicolon. So these changes we save to the periodogram as a function here. Now this function has been developed. Now we can call this function to the script here. So already the calling syntax we have written over here. Now the x that has been developed into the above part that we are going to make the use of, the values 10 and 15 are specified for n1 and n2. Now the spectral estimation can be carried out by this single step here, and after the spectral estimation has been carried out, we have to plot the estimate here. So here we write the module to be plotting the spectral estimate. So for plotting the spectral estimate, so as the stem function we have used for plotting of which particular random process we have been using for the spectral estimation here. So we want a separate window, that is why we make the use of the keyword figure. Next to that simple plot command can also be used here. And to this plot command, we can provide the input capital P small x here. So this particular plot command will help us to plot the power spectral estimate that we obtained by the use of periodogram that we have developed in this particular function here. So let us execute it, saving the changes and running this particular program. Now you can see into the workspace onto the right hand side that it was only one the variable, that it was x, the random process here. Now there is another variable produced with the dimensions 1024 by 1 of the type double, and it has the name px. So this function periodogram.m has been called, and it has produced the output that has been saved into this variable px here. And now with the help of this particular line, it has been plotted. Now this is the first figure. This is the input discrete time random process x of n in general, and to this discrete time random process we have obtained the power spectral estimate that has been plotted in this particular graph here. Now you can see the horizontal axis where we have 0 to 1200 here, and here it is the point exactly of 1024 here. So at 1020 value we have the last amplitude 0.00, for 23 we have 0.001317 here. So the variation of the values that we can see into the Fourier domain that has been plotted here. The amplitude levels, we start at 0, the intersection of the horizontal and vertical axis here, and at max we have the 2.5 into the graph range, whereas here we have 2.227. So at this peak here we have the maximum value, here we can see 2.226 here. So this is one way of simply plotting whatever the spectral estimate that we have generated by the use of periodogram technique. Another way, we can also make the use of spectrum estimate into the decibels here. So here this first task, that is simply the use of plot command, we shall be specifying here with the name making a plot of spectrum estimate. Next to that we shall take another task. It will be quite different. Into the decibels we have to write, so we shall be writing to plot the in decibels here. So for plotting the spectrum into the decibels, we again make the use of figure command and then plot command, whereas the input is not simply the px here, but now this time for decibels we carry out 10 in multiplication to the multiplication by the asterisk sign logarithm base to the 10. The input here it is capital Px here. Now with the use of the same, as we save here, and if we run the program, now you can see here it is the first window, as we are using the function RALDN. So that time the input discrete time random process is getting changed a little bit, as it is the characteristic of the same function. So this window I am going to close, and this is the another window where into the decibels onto the vertical axis we have plotted the values for the power spectral density estimate here. Onto the horizontal axis again you can go for the values plotted from 0 to 1024 here, the maximum range of the graph that has been shown up to the 1200 here. And into the decibels, the values onto the positive side we have 5, into the negative side we extend -5, -10, -15, -20 up to -25 here. The highest peak here we find at the amplitude 2.761, whereas the least values are there. The values can be seen with the amplitudes -13.9, and here it is approximately -13.85 here. So this is also the another way to have plotting of the spectrum in decibels here. Now next to that, if we can make the use of Nyquist frequency here, now we can have the task here, and this task will be to have the labeling of the frequency axis into the hertz here. So to label frequency axis in hertz here, so H suffix said here, we take the Nyquist frequency, simply for example computed 5 in multiplication 2, here we take the range 0 to, we extend 1023, so total 1024 samples here, and this is divided by 1024. So this is the definition of the f that we are going to make helpful for plotting. So again making the use of figure command, and then it will be the plot, and for this plot we have f comma capital P small x here. So this completes our task, and let us see what way the result is plotted here. So if we run it, so here first of all we have the another discrete time random process, and for this discrete time random process plotted here, we have this particular spectral density estimate shown in this particular graph. Now you can see the change onto the horizontal axis, as we have the values from 0, 0.51 up to the maximum 5 here. The intervals are of the half value here, and these are all concerned to the frequency, and the maximum range is up to 5 here. The amplitude levels that you can see marked from 0 to the maximum 4.5 here. So this way any discrete time random process can be generated here. These are the various ways we have seen to have generation of the random process, and this is what the simple function called as the periodogram that we have formulated by the use of the understanding from the previous video, where we have mathematically shown the power spectral density estimate, and by calling this particular function into this main script here, we can finally plot it by the various ways, the simplest ways, or into the decibel forms, or by the use of frequency values onto the horizontal axis. We can plot this spectral estimate by the use of periodogram technique here.